Hello everyone, I'm James Jose Baclan and I'll be answering questions 4, 25, 46, 67, and 88. So question 5 is, now the first thing we do is to find the current, the field current, and that's equals to voltage of the motor over the field resistance, that's equals to 230 volts over 115 ohms, that's equals to 2 amperes. Now we use that 2 amperes in getting the current, the current at full load of the armature, and that's equals to 57.1 minus 2, that's equals to 55.1 amperes. We use that current in finding the power of the armature at full load, that's equals to I squared times R, and our I is 55.1 and our R is 0.13, which is the resistance of the armature. We should have a power of 394.7 watts. Now we find the PSH, and that's equals to the voltage of the motor times 2, because power is V times I. This is V, this is our I. We have 460 watts. Now our power input is the voltage of the motor times the current of the motor. We have 13,130 watts. Now for our power output, power output is given, and that's 15 horsepower. To convert that to watts, you multiply it to 746. You should have a power of 11,190 watts. Now next thing is, after getting all that power, we find a stray power, that's equals to power input minus power output minus our PSH and the our power of the armature at full load. So subtract that to the power input, we have a stray power of 1088.3 watts, and that 1088.3 watts we will need that to find the current at no load, the circuit. Now we have the power stray is equals to the voltage times the current passing through the motor minus the current passing to the armature times its resistance, which is I squared times R. So after that, we should have a current at no load of the armature of 4.745 amperes. Now we should be able to find our speed at no load by using the formula. Speed at no load is equals to the speed of the motor times the voltage at no load over voltage at full load, and our RPM of the motor is 1400 times voltage at full load, voltage at no load, that's equals to power stray over our current at no load. We should have 229.383 volts, and our volts at full load is equals to 230, which is the voltage of the motor minus the current of our armature at full load times the resistance of that. We should get we should be able to get 222.837 volts. Now we do the math, then our no load, the speed of our no load should be 1441.126 RPM. So question number 5 is, when a series DC motor is started with no load, then there will be a rapid increase in its EMF. That's because the current becomes low and the counter EMF produced by the field winding is too weak. That's why the counter EMF should be sufficient enough to balance the voltage supply, and it's not advisable to start the series connection without load because the motor will be destroyed. So question 46, And the answer is induced EMF, as it is the fundamental phenomenon for all DC machines, whether it's DC generator or DC motor. And both have the same equation wherein it is equals to P times Z times flux per pole times N over 60A, where P is the number of poles and Z is the total number of armature conductors, and N is the speed of the armature in RPM, and A is the number of parallel paths in the armature winding. So question 67. For question 67, we use the formula torque 1 over torque 2 is equals to current 1 over current 2. We have the given torque 1, which is 54 Newton meter, and the current 1, which is 10 amperes, and the second current is 20 amperes. Now we cross multiply this 20 and 54. We have 54 times 20, then the torque 2 times 10, torque 2 times 10, then 54 times 20, we have 1080, then over 10 to get to cancel out this 10 here. We now have torque 2 is equals to 108 Newton meter. Question 88. Now, Hopkinson's test is used in identifying the efficiency of a DC machine, and you need two identical machines wherein the other machine is used as a generator to provide or supply a mechanical power to the motor, and the other one is used as the motor that's gonna drive the generator. And the disadvantage is that it's difficult to find two identical machines.